Welcome to Severe Weather with Mr. CB. This is lesson one. We're going to be talking about some kind of random things, but it will be important to start. First, let's talk about virtual temperature, represented as TV. This is the temperature that dry air would be if its pressure and density were equal to that of the sample of moist air. So that might not make sense. So let's talk about that in a little bit more detail. This paragraph will help us know. Um, Basically, this is a correction to better represent how a parcel would respond to an environment that does have moisture, because there likely is some moisture at the surface. So remember, when a parcel rises, it cools by first the dry adiabatic lapse rate, then when it hits the LCL, it switches to the wet adiabatic lapse rate. But the truth is, it's not going to be completely unsaturated. Um, it's not going to necessarily be unsaturated at the surface. We will sometimes have some moisture to a certain extent. So to correct for that, we use this temperature instead sometimes, and it is greater, always greater than or equal to um, the environmental temperature. So it helps us compare. And then it's important to know that moist and warm air are less dense than dry and cool air. And why is that? Well, we know that moist and warm air want to rise, so if they're able to rise, they must be less dense. Latent heat. We've already talked about this in weather analysis if you watch my videos, but it is the heat that is absorbed or released by phase change. So it's basically phase change heat. And the six different processes that we have for phase changes, we have MES that are the cooling processes, which is melting, evaporation, saturation. Those are cooling processes. FDC are the warming processes, freezing, deposition, and condensation. Um, I said saturation for the S, sublimation. I'm sorry about that. I don't know what I'm doing. Um, so remember that might sound counterintuitive that um, freezing is a warming process and melting is cooling process, but that goes back to the fact that you have to think about, are we talking about the parcel or the environment? And um, that's not something I'm going to get into right now because we already talked about that in the weather analysis, but that's not even really the purpose of this right now anyways. But just remember that it is counterintuitive. Condensation, which is a warming process, is going to be very important for this class for severe weather. Now, there's two other temperatures that we want to talk about, which is potential temperature and equivalent potential temperature. So potential temperature is represented by theta, and it's the temperature that a parcel would have to be brought, or would, sorry, the temperature a parcel would have if it was brought dry adiabatically to a standard reference pressure, corresponding to a level in the atmosphere, which is typically 1,000 millibars. So now we're able to compare amounts of energy in two locations. We're basically changing the temperature of something to make it apples to apples. Um, so maybe we have a given temperature, but we might increase or decrease it to get to the potential temperature um, to show what it would be like at a similar level as another location. And that's how we're able to determine potential energy to an extent. So if you think about it, basically, let's say you have one location that's 72 and one location that's 67. You might assume, warmer. is going to have more energy, but you need to think about the potential temperature for potential energy that we might have. And then equivalent potential energy is represented as theta E, which is the temperature that a parcel would have if all of its water vapor uh, condensed, meaning that latent heat is released, and the dry air was dry adiabatically brought to a standard pressure. Basically, this is a better indicator of stability because now the difference between this and just potential energy is now we're considering moisture. And so we're changing the temperature even more to account for moisture differences. Um, and you can see this in, well, actually, we're not going to sh show that right now because it would be better if I actually had an example for that. Um, but some models do display this as lines that gray lines that are in Kelvin. Whoa, I didn't know I could do that. Look at that. Oh, it's weird. Okay, well, that's actually it for the video. So there I go.